This video is going to work through an example or two of finding electric fields. So here's what we have. We know that the electric field strength is equal to KQ over R squared. So one simple problem that we can solve would look like this. If I've got a coordinate axis, because we pretty much always have a coordinate axis, if I've got a coordinate axis like this and I have a charge of, we'll say Q equals 2 coulombs, microcoulombs, right here at the origin, maybe I would like to find my electric field here. And we'll say this is X equals 4 meters. Right, we're going to find the electric field there. So we're just going to say our electric field strength is going to be KQ over R squared, and I can plug in some numbers. I've got an 8.99 times 10 to the 9th Newton meters squared per coulomb squared. Q is a 2 times 10 to the minus 6th coulombs, and I'm going to divide that by, and I said 4 meters, so 4 meters squared. When I do that, I get an answer of 11,250. That is newtons per coulomb. I would want some kind of a direction on this. This is a positive charge, and a positive charge is a field pusher. So this will push out electric fields radially outward from itself. At the location that I'm looking at, that would be to the right. So I'm going to say that my electric field looks like this number in the X direction. That's about as simple as we can come up with. So let's look at a little bit more complicated. One might be this. Maybe I have these two charges. So let's have an x-axis. We'll stick a positive charge here. Q equals, let's stick with our 2 microcoulombs, and we can stick a charge here. Let's say Q equals -4 microcoulombs. That can be good. And I want to know, where can I put a third charge so that it feels no net electric field? This extends back, of course. Where can I put a third charge so that it feels no net electric field? So I'm going to put a charge somewhere, and I'm going to first label these different regions. So I'm going to have region 1 over here on the left, and that's going to extend to the left of my positive charge. To the right of my negative charge, I'm going to have region 3, because region 2 can go between them, and that way they're in order. So I want to look at each of these regions and see what's going on. So if I pick a spot here in region 2, region 2 feels an electric field from charge 1. I'm going to call these 1 and 2. From charge 1, it's going to feel an electric field that points to the right. Because charge 1 is positive, it's a field pusher, so it pushes to the right. There's my E1. Charge 2 is a negative charge, that's a puller. So I'm going to get an E2 that points to the right. There's no way for those two to cancel, so I know region 2 is not the answer. Let's look at region 1. In region 1, I get, here's my positive charge is a pusher, so this is going to go this way. And now I want to look at it a little bit. In region 1, I am close to the weak charge and far from the strong charge. Because my electric field is KQ over R squared, if I've got a bigger Q, right, I'm trying to match these effectively. KQ 1 over R1 squared is going to be KQ2 over R2 squared. If if Q1 is smaller than Q2, then R1 has to be smaller than R2. So I need to be looking in region 1 to make this work. So I know that I want region 1. Now I'm going to do some erasing, and then I'll come back and start the problem. So I'm looking over in region 1. In region 1, I've got my location marked, and I'm going to say that the distance from my location to charge 1, I'm going to call that distance x. So then the distance from here to the far end, I need a distance between these charges. Let's say this is, we'll stick with 2 meters. So this is going to be x plus 2 meters. Now I can write these things out a little bit. So my electric field from 1 is going to be k q1 over x squared, and that's going to point to the left. My electric field from 2 is going to be k q2 over 2 meters plus x squared, and that's going to point to the right. And if I want my net field to be 0, I need these to cancel. So I'm going to set these equal to each other. K q1 over x squared equals k q2 over 2 meters plus x squared. I can cancel out the k. I can actually cancel out the micro part of these because the times 10 to the minus 6 is going to cancel. And solving this, I'm going to have a q1 times 2 meters plus x squared equals q2 times x squared. I'm looking at absolute values all the way through, so I don't care about this thing being negative. And now I'm going to expand this out. Get a q1 times 4 meters squared. I'm going to get a q1 times 2x. And I'm going to get a q1 times x squared equals q2 times x squared. All I did was expand out the parentheses. And then I'm going to move everything over to one side. So I'm going to subtract this over. I'm going to get an x squared times q1 minus q2. I'm going to get an x times 2q1, and I'm going to get a non-x term that's just q1 times 4 square meters equals 0. When I solve this using a quadratic equation, I get two answers. I get a negative 0.83 meters, and I get a 4.83 meters. And now I have to think about this a little bit. The negative answer here doesn't make sense, right? I said x was this distance. I just said it was a distance. I can't have a negative distance. A negative x value would put me over here somewhere in region 2, which I don't like. So 4.83 meters to the left of Q1, that's going to be my spot. That's how I find electric fields. I can do one more thing with them. I can say I have a charge here, let's say positive 2 microcoulombs. I have a charge here, let's go negative 2 microcoulombs. We're going to have this be 3 meters, and then 4 meters away I would like to find the electric field. Call this thing Q1, call this thing Q2. I'm going to find both of my electric field strengths first. And then I'm going to break these into components, or at least break E2 into components. Now it points up and to the left, and I can say right here I've got this right triangle, so let's use it. There's an angle, so that's going to be the same as my angle here when I try and break this thing into components. I know that the cosine of my angle is 4 over 5, because 4 and 5. I know the sine of my angle is 3 over 5. So I can find the x and y components. And now I can add these up in a table. And then I can reconstruct this vector. I've got an x component that points to the right. I've got a y component that points up. So I get a hypotenuse that I can get from Pythagorean theorem. And I get 699 newtons per coulomb. And I get an angle that I can get from an inverse tangent. And there I get 38.2 degrees, which I guess would be above the positive horizontal, or maybe like north of east if we're working in that coordinate system. So that's how I add electric field vectors that are not necessarily parallel. It's the same as how I've done vector addition all along.